All right, my friends, let's get this started. Ugh. All right, let's do it. Okay, so what we're gonna crank on today is the chapter. I think it's chapter 3 stuff. So so let me hear. So no real announcements right now. Just kind of stay in the course. The homeworks are due tonight. Two and was it homeworks 2 and 3 are due tonight, and then homework 4 is going up tonight and be doing a week from today. So, but what we're going to do today is the actual content of what we're going through, our course content, like the meat of the content is really short. So we're going to have a fair amount of time at the end of class today to go over, well, you can either bust out, or if you want to stick around, we're going to hammer through some more decibel questions and problems. Cause I know that there's some questions, just cause I know we've just been blasting through this stuff so quickly that I know it's like just tearing people's heads off. So I want to slow it down a little bit and, like go demonstrate, work through some problems and kind of try and work through those a few more times. So that's what we're just going to dedicate the rest of this class for. So really we only have chapter 3 stuff, which is really pretty short. And that's what we're going to go on today. So, oh, that's right. Yeah, thank you. Cause I didn't get it up until Friday. So like I said, but no, I was just thinking of the normal schedule. So when I post a homework, I will always give you a week to do it. Like, so from when I posted it, and I didn't get it posted till last Friday. So that's why you have those going up right there. So, we'll go through, like, I'm not going to do the exact numbers on the homework questions, but I can look at them. We can do alternative versions of those that can help you, like, along with those, if there's any snags. And also we're going to have some coming up. So the homework that's going up tonight is going to be based on the stuff we talked about today, as well as some of the decibel stuff that we talked about last class as well. So, yep. So yeah, we'll get to that in a little bit. So we'll talk about that at the end of class today, about all the homework stuff. So cool. All right. Cool. Let's do it. So we want to do is we're going to talk about this idea of sound in the free field, and what we're trying to do is, as I guess, kind of like the arc of what we're trying to understand here is, we started off with just understanding kind of like the nature of sound, how sound waves move and pass through the air. And we're going to start building stuff up when we start talking about reflections and that sort of stuff, and how sound interacts with space. But first, what we do is we just wanted to start talking about sound moving through air. And then the second one with chapter 2 is we start talking about levels. And we're going to deal a lot more with levels starting next week too. So we're not going to be doing like hardcore dB, but I do want you to understand like loudness and levels and human perception and how the human anatomy works, so that we understand and have an appreciation for the anatomy and physiology and the psychoacoustics of how sound works and how music works. So we're not really going to go to the psychoacoustics on music, but we'll touch on that a little bit. But what we're trying to do is develop this just understanding of how sound interacts with our world. And yeah, at this point we've talked about just the nature of sound, and then we started talking about levels and decibels last time, which is kind of a sidestep departure. And now I want to reel this back in and start talking about how sound moves through space, and this notion of what we call sound in the free field. So so that's the chapter. So chapter 3. So what we say is the free field. So the free field is essentially like idealized conditions. So free field means just sound without reflections. That's really what it means. So if we were to set up a speaker, and this doesn't even work, a speaker doesn't even really count for this, but well, I guess what we're saying is, what we're trying to do is we're trying to create a simplified model. So we want to understand how sound propagates and expands through space, so we can just understand how it works before we start adding more complex situations like rooms and interior structures and outdoor venues and some of these other kind of situations. We want to develop a simplified version of it, and then we'll add complexity to it later. And the most simple version of like a sound in space is going to be a free field. And so, like I said, it's going to be like sound without any reflection. But if we imagine it like an idealized sound source. So when I say an idealized sound source, means like something that sounds a speaker. And so when I say a speaker, I don't mean like a normal speaker. So a normal speaker, when I have a speaker, if you point the speaker away from you, it's going to be quieter, although you're going to be able to hear the low frequencies. And then if I turn it towards you, it's going to be a lot louder. So that, to me, that says that it's emanating, it has a directionality, a directivity, and like has directivity. So that if I move it away from you, it's not going to get as much energy, and if I point it towards you, it's going to have more energy. So an idealized speaker like is going to be one that emanates in a spherical pattern. So that's what we're talking about right now. Is we have a sound source that emanates in a sphere without any reflections. If you want to think about it, it's like you can imagine it thinking like and usually what I do is I'll have like a light bulb. So if you want to think about it like a light bulb, well, let's use the sun as an example. So the sun is, and it's not emanating exactly in a spherical pattern. You have dark spots and you have all these other kind of things happening, solar winds and all this sort of stuff happening. But if we imagine it that the light off of the sun is emanating out as a sphere. So we can use light like as an analogy here. So if we think about the sound that's pulling off of a sphere, it's going to be expanding out and expanding out, expanding out. And then we're on Earth, like all the way out here, and it's just catching a tiny fraction of that light that's emanating off the sun. But it's enough to cook me, when I go outside, and if I don't wear sunscreen, me and the sun don't get along so good. So I get cooked, like, in just about, like, you think about me compared to how much energy I'm pulling off that sun. That sun is emanating a spherical pattern, and I'm just a small, tiny, weeny speck, and that's still enough to cook me. It's pretty impressive to think about how much energy the sun is outputting in terms of radiation. But if we think about that, and that we'll continue on with that analogy here coming up. But again, we think about that emanating as a sphere. Now, we don't have any real speakers that can do that. I mean, there are people that have come up with some pretty kind of clever ideas on speakers, on how to make speakers emanate as a sphere, where you want it to emanate essentially as a point source. And a point source meaning all the sound emanates as a sphere from a single point. But in real world, we have speakers have directionality and that sort of thing. And then also in real world, also we have reflections like the ground. Like, so usually there's going to be reflected off the ground. But again, to understand kind of what we want to look for, what we're trying to understand here, let's simplify this down and imagine that we have a spherical speaker with no reflections. That's what we're looking for. So there's no absorption, there's no like diffraction, diffusion, any of that kind of stuff. So, and then what we'll do is we'll develop that model, and then we'll reel it into this kind of, into this more real world conditions here. So we call the sound intensity in the free field here. So if we look at energy and distance here, so this is kind of like looking at that light model. So this is true for any kind of like spherical emanation. But if we look at this right here, so imagine this is the sun, and what we're doing here is these are grids on the surface area of a sphere. So if we can imagine this, that we have this energy off a single point, and it's emanating as a sphere. Now, if I were to say collect all the energy off this, we'll call this A1, A2, A3, A4, these different like radii right here, like so off this right here, and we're showing it as a two-dimensional picture, right? Because like it's hard to draw spheres on a two-dimensional, like we're looking on a screen right here. But if I were to look at this like as like thinking about it as a blowing up of a balloon, actually that's actually a pretty good example. So we use like the material of a balloon as kind of our energy. But I'll explain that here in a second. So if we've got this, it looks like a circle, but we imagine it's a sphere. And what these are right here is this is like a partial cutaway of that sphere that we're seeing right there. So imagine this as a sphere that's going out right here. And if we look at this and this energy, and so like we think about this sound as energy coming off, or light, or whatever you want to call it. That energy, if I sum up all of the energy that's on that sphere, like as that energy that's coming off that sphere, we'll just call it 1. Just because I feel like calling it 1. It doesn't matter what it is. 1 what? Doesn't matter. It's just 1. One, the sum of all this. But then when, oh, sorry, I see this picture right here. Can you hear some of the sound when the direction of the speaker's faced away from you in an open field? It's a very good question, and we're going to answer that in very good detail coming when we start talking about diffraction and reflection. So we will answer. I'm going to save that one for later. But in a nutshell, the low frequencies bend around, and the low frequencies do emanate as a sphere, but the high frequencies beam. Low frequencies bend, high frequencies beam. But that's called diffraction. And we're going to deal with that in great detail coming up. So again, going back to this idea of a sphere right here, that a sphere of this diameter, or this radius, so a sphere of this radius, and I add up all the energy on there to be like, we'll just call it an energy of 1. Then if I go to this A2, and as it spins out, and I sum up all of the energy on this A2, what's the total like sum of all the energy on that? Anybody got any ideas? If I call this one 1, what is this one? It's 1. Yeah. So in other words, I mean, we're not going to go into like Newton's laws or any of that kind of stuff, but basically saying it's like all it is just a larger sphere. But the energy is distributed over a larger area because the sphere grew. So it's because we call it conservation of energy, I have the same amount of energy from when I came off this point the same amount of energy there, the same amount of energy on A2, the same amount of energy on A3, and the same amount of energy on A4. So it's all the same energy, it's just, it's all there. But it's distributed over a much larger surface area. And so that's what we're looking at right here. Is we can see that if we go from A1 to A2, that this like little patch, if I were to project this patch, and what they're doing is they're like taking this patch and they're projecting it down in from a point all the way out here, that this patch now takes up is 4 times as big. So if I doubled my distance right here from R to R, then my area is now gone up by a factor of 4. Interesting. So in other words, so if I go from here to here, I doubled my distance, but my area went up by 4. And if I go from A1 to A3, so if I tripled my distance, so in other words, from R to 3R, it's going to triple my distance. Now it's gone up by a factor of 9. So it's 9. So, and then if we go all the way up to right here, it's a 4x4 grid right here. So that is 16. So that basically, if I went 4 times the distance, it's 16 times greater area. Or we could say that each patch, so we imagine this patch, and this patch are all the same area. It's hard to see it. They didn't really draw it to scale very well, good to scale here. But this patch and this patch are the same size, that this patch is now 1/16. So in other words, the area, an area of the same size is 1/16. And if we think about something like our eardrum, for instance, so our eardrum is a fixed size. So it's a fixed patch, right? So it would make sense for us to kind of think about this as like a fixed patch. So rather than thinking about that, this is now grown to be 16 times its original size, we could say that the energy is now that's hitting this is 1/16 what it originally was of the same patch. So if we think about it again, like our eardrum is a fixed size. So if I move closer and further away from it, what I can say is that as I double my distance, it went down by a factor of 4, like the intensity or the energy hitting my ear. So the energy is watts per meter squared. So it's the energy per area. So what it's saying is that as I move, and this goes along with our intuition, right? If I move away from a sound source, it gets quieter. Duh. Yeah, why? Because we're farther from it. Well, why does it get quieter when we're farther from it? Because we're only getting less of that energy that's emanating off of that virtual sphere, so to speak. So we're only picking up smaller parts of it. And that's kind of one of those cool little things like, whoa, I didn't really ever think about that. It's totally true though. As I get further away from it, why does it get quieter? Well, that's because as the energy that's emanating on it is being distributed over a larger area, yet your eardrum is staying the same size. So therefore, you're picking up less of the energy. And again, that goes right along with our intuition. We're like, yeah, duh. When I get quiet, when I move away from it, it gets quieter. But here's like the scientific reason for that, and it's kind of cool when you start to like think about that. And I don't know, this is how I roll when I think about like sound and acoustics and sound interacting. I like to imagine like the physical waves and how they're moving around and the areas and microphones and I don't know all these different things. I think it's kind of just fascinating to think about it in terms of a physical sense. So that's kind of what I want you, well, among other things out of this class, is to start to get an appreciation for like what these sounds look like and how they work. But if we imagine this though, like, so we can see that this is an impressive rate of drop off. So in other words, every time I double, it goes down. It goes down by a factor of 4. So if I go here to here and here to here, so if I went A2 to A4, that's a doubling of a distance. So it went from 4 to 16. So 1 to 4 to 16. So if I went for 8 times the distance, it would go down to 32, like 32 squares. So was that right? 8 by 8? No, 64. My bad. So gets pretty intense, or not intense. It gets a lot less intense. Pretty interesting to think about there. Yeah. So so don't write this down. I'm just going to show you this, because I don't want you to try to think that there's a lot of math going on here. We can look at the math and we're going to talk about it, but I don't want you to write it down, because it's not that I don't want you to remember it, but I want you to remember why, not the actual math itself. So we have this thing, what we call the inverse square law. So when we looked at this, oh yeah, that's right. Okay. I was thinking about the volume of the sphere. So let's look at this. We call this intensity. So intensity of a sound source. So intensity, if you kind of recall what we were talking about last class, intensity is defined as watts per meter squared. So watts is the energy and the meter squared is the area, is the area. So it says how much energy per area is it hitting right there. And then if we think about the meter squared, the watts per meter squared, so the area on the bottom there, we can imagine that as being the sphere. So this is the area of a sphere. So if we want to figure out the surface area of a sphere, is 4 pi r squared. So all we need to know is the radius, and then we can figure out what the total surface area of that is. And then if we have the wattage, we can figure out how much energy is distributed over that entire sphere. And that's all well and fine. We don't really actually need to go through and do these calculations. That's not really that important. But what we want to do is this relationship here. And what we can see here is that when we have the square root the squared value on the bottom here, is that every time this relationship right here, every time we double it, it goes up by a factor of 4. If I go triple it, it goes up by a factor of 9. So that's basically, this is right here explaining why it's growing so fast, or why our patches are getting so small so quickly there. It's because this is the squared value of this thing. So in other words, by increasing the area of by increasing the radius of my sphere a little bit, my surface area increases a lot. So a small increase in radius results in a large increase in sphere area. So that's what I want to take away from this thing right here. So what this tells us, though, whoops, whoa, I went to the end there by accident. My bad. So what this tells us is that doubling the intensity sound source drops the intensity by 4 times. So that's the thing I want you to remember off this slide. That's the important bit right there. That's the thing to remember. Doubling of sound source distance drops intensity by a factor of 4. Okay, so what does that mean for us? Like that's the thing I want to say. So doubling the source drops intensity by a factor of 4, or say 4 times. Oh, the reason for that is because it drops intensity by 4 times, because again, our area of our ear stays the same. So basically our intensity drops. So let's look at this. This is pulled from the book. So what we see here is if I double my distance, it drops by 6 dB. That's interesting. So what we're saying there is that we drop by a factor of, let's see. Yeah, so it drops by a factor of 4. Let me think about this. So what they're saying, there's one little bit of fuzziness here that's confusing me, and I'll explain it. And if you want to help me out with this, you can. But basically what we can say here is by doubling the distance, it's going to drop by 6 decibels. So every time I double my distance, it drops by 6 decibels. So if I go from, say, 2 meters to 4 meters, it's a 6 dB drop. If I go from 4 meters to 8 meters, it's a 6 dB drop. If I go from 50 meters to 100 meters, it's a 6 dB drop. So what we see is that even though it looked like, we can see this, that like it seems strange that every time I double, so this is like on a logarithmic scale. So basically 1 to 2 to 4 to 8 to 16 to 32 to 64. So that basically what it does is it drops off quickly in the beginning, but doesn't drop off very much as I double. So in other words, the difference between, say, 50 and 100 is only 6 decibels, and 100 to 200 is only 6 decibel drop. So that kind of like, it's kind of impressive that it's only a 6 dB drop per doubling. So in the beginning, it drops very quickly. So if I go from 1 to 2 or 2 to 4, it drops 6 dB each of those times. But now as I get further away, it seems to drop less and less and less. So if we think about, again, in terms of human perception, in terms of light, that that every time we double our distance, it only drops by 6 decibels. So, and this is kind of crazy. I mean, you think about, like, you know, when those campfire nights, when you're sitting out, like, looking up at the stars, and you're thinking about like the mind-boggling, like, it's so hard for us, our human brains, to understand distance, like in terms of light years. We use light year as a distance, but like when we think about these, like how far away those stars are, and if you imagine like those super far distant stars that are in the Milky Way, if you pick out one star and you imagine the energy coming off of that star, how much that little sliver of light that you're actually able to perceive, it's insane that you're able to see that it traveled so far. And you look at that entire sphere, how much of that little point of that sphere that you're sitting on that you're able to perceive with your eyeballs is just like I don't know. It's like that's those kind of trippy thoughts, but like it's when you start to like understand the actual scale of space and like I don't know if anybody's ever read Short History of Nearly Everything by Bill Bryson. It's a really fun book. I loved it, I thought. But anyway, the whole first part of I think it's the first chapter or so. It's been years since I read it, but he tries really hard to explain how far away stuff is, like how big space really is, and it's like it's literally mind-boggling. It boggles your mind how big space is. And when we watch all these sci-fi shows and everything like that, and people hopping around to different planets and all that kind of thing, you're like, oh no, like this isn't going to work. Us traveling to Mars, that's all well and cool, but us traveling to another galaxy or to another solar system, it's like we got to bend some physics laws with wormholes and all that kind of stuff, which gets into sci-fi territory for now. But it's crazy to think about that. But the same thing happens. Like let's reel that back in and talk about this in terms of like light, or start talking about this in terms of sound. So that means if I go walk away from something, that it drops very quickly in the beginning, but yet I'm still able to perceive it pretty far away, because it's still, even if it drops, like, I mean, we'd have to say 60 dB drop is a pretty good drop to be like inaudible. So I have to be pretty freaking far to go. 60 dB is like 10, like, I could do the math on it, but I don't really feel like doing it. Basically, you can still hear stuff, even if it's faint, you'll be able to hear stuff very, very, very far away, because that's fear. Now, that's of course talking about things in like, I'm talking about stuff in idealized conditions. So space is actually a pretty good example for doing like this kind of thing, like this growth of idealized conditions. But actually in real world, we have reflections. So if you imagine, say, let's put a PA speaker up on a pole, and we're trying to create this. Well, the truth is, all that energy first off, a speaker is going to be directing the energy in one direction. But even if we created a speaker that had a bunch of speakers in an array, so it acts like a sphere, if I were to do that, the energy coming off that speaker up on a pole is still going to reflect off the ground. And so therefore, it's not going to be quite the same thing. So we're doing this in an idealized condition, but in real world, things change a little bit there. So let's do this. Let's do a question with this. This is not a clicker or anything like that. There's no clickers today. Cool. So if I start with an intensity of 0.001 watts per meter squared at 4 meters, then what will be the dB change at 8 meters? Well, this looks complicated. And so the reason I'm telling you this is because I want you to, like, we call this the inverse square law, is all I want you to do is remember that every time I double my distance, my intensity goes down by a factor of 4, which is also a 6 decibel change. So in other words, I could say if I start at 1.001 watt per meter squared, in fact, if I wanted to, I could figure out what that is in decibels, because we know with that, like, we can refer back to 1 times 10 to the negative 12 as being our reference value and figure out what this is, and we can figure out what the dBSPL is, but we don't need to. This question looks a lot more complicated than it really is. All I'm asking you to do is go from 4 to 8 meters, which means I doubled my distance. So the answer would be 6 dB. But let's actually do it. So we know this because I told you this. So right here, what I'm going to do is I go dB equals 10 log I2. These are supposed to be subs, I2 over I1. I don't know. I must have missed that. My bad. So it's I2 over I1. So because we know that when we go this is our initial distance right here. So this is our intensity, our I1. Then what's our I2? Well, we know that by doubling our distance, it goes down by a factor of 4. So in other words, I divide this number by 4 is 0.00025 right here. And so 0.0025 divided by 0.01 is a quarter of the value. Yep. So then I have the log value of 0.25 times 10, which is negative 0.6 times 10, 6 decibels. So it's so we say the dB is 6 decibels. So it's a 6 decibel drop every time I double. So that's what I want you to remember right there. So like basically dropping like every time I double my distance, it drops 6 decibels. That's all you really need to know. Like or we could say that it goes down by so there's 2 ways we can say it. By doubling your distance, it goes down by a factor of 4. But we can also mathematically show that dropping by a factor of 4 is a 6 decibel drop. Cool. So that's all there really is to it. We could also do the factor of 9. You know, if you triple your distance, it goes down by a factor of 9, and if you quadruple your distance, it goes down by a factor of 16. But I mean, so 1/16 is going to be a 12 dB drop, or sorry, yeah. Yeah, you can do all the math on this stuff, but really the bottom line is all I want you to remember is that every time I double my distance, it goes drop by 6 dB. So what is 6 dB? Like, what does 6 dB actually sound like? Let's make up a quick example for this thing. Let me go to, I was gonna build one out, but I'm gonna do this with Max, just because I like doing it. I think working with Max is fun. If you ever have any more classes with me, which you will, if you're in this class, I usually teach all the critical listening classes. So I'll be teaching critical listening next year, and that's the class you take after this. So you'll be going into AP3 and critical listening next semester usually. And I use this programming environment called Max. This computer doesn't have it registered on it. Come on. Need to sign in real quick. Cool. So what I'm gonna do is Max, like, I'm just gonna introduce this to you. You'll see, you'll if you have classes with me, I use this a lot in a lot of my classes. But Max is basically a programming environment, but it's specifically built for like doing audio and video visuals and interactive and media. If you work in Ableton, Max for Live, so you can actually run this inside of Max, or you can run this inside of Ableton. So I write Ableton plugins with this stuff. So, but the cool thing is if you can think it, you can make it. But it's really good at doing stuff like audio stuff. So what I'm going to do is I'm going to create, let's just do a noise. So I'm going to create, actually let's do pink noise. So I'm going to create a pink noise generator. Live.gain. If you work with Ableton, you're used to seeing these kind of looking things. Let's make it so it looks nice and clean. And let's do Easy DAC. So you can hear it. It's got a volume knob. So right now, all I did was I created a noise generator right here, a volume knob, and then an output so you can actually hear it. And let's send it through Zoom. Let's see. Send my audio output, Zoom audio, cool. And what I'm gonna do now is let's do minus, I'm gonna add a double thing here. I'm gonna go, this doesn't really matter. This is not that important to you. What I'm actually doing right here, actually this is kind of cool. This is kind of neat to think about for a second. 0.5. So, oops, I'm gonna multiply the incoming value by 0.5. So this, what I'm doing here is I'm taking any of the gain or any of the, of the sound coming through here, and I'm multiplying it by the amplitude by 0.5. What is the 0.5? So if we have our gain, that's a 6 dB drop as well. So if I drop, so in other words, if I drop half of my amplitude, dropping half of my amplitude is a 6 dB drop. So what I'm doing right here is I'm adding a 6 decibel drop, and then I'm gonna have another gain on top of this right here. So just to prove this, let's just get this thing working. You hearing that? Cool. Good old pink noise. So I just didn't want this thing, even though I have this thing going full scale, it's not actually output. Like, I don't want it to tear your heads off and be too loud right there. Okay, so what I'm gonna do is I'm gonna throw a thing on here that says 0. So I'm gonna throw some, like, essentially it's kind of like, you can think about this like an automation system. So I want to just quickly turn this to 0, and then I'm going to quickly turn this to -6. Because what we're trying to do here is I want to give you the impression of what a 6 decibel drop sounds like. Okay, so this -70 is essentially like is essentially what we call negative infinity. So basically beyond this is our dB drop. So just like what I was talking about before, this is kind of cool. We can look at like this this gain right here, this negative 48, what it says is that it's dropping the input, the I1 to I, well, in this case it's V1, V2, that it's basically dropping it by 48 decibels. So the incoming value is being reduced by 50 values. So what I want to ask you, remember, whenever you see the term decibels, what is it comparing? A decibel is always a comparison. So what it's doing, this value right here is comparing the input value to the output value. So here's the input, the gain coming on the input, and this is what it's coming out. It's dropping it. The input to the output level is changed by negative 48 dB. And you could go back and figure out by how much that ratio really is. You could put negative 48 equals 20 V log L2 over L1 and figure out what the ratio is of that. And that's actually pretty interesting. Maybe we'll do that at the end of class today. We'll spend some more time on that. But what's interesting here is what I want to do is, so I have negative 70 is equates to negative infinity, because in that case where it's saying the denominator, or sorry, the numerator value is getting so small that it basically approaches negative infinity. But that's just mathy stuff. We don't really care about that right now. What I care about right now is I'm going to hit the 0. So what the 0 does, it says exactly what comes in is what's going to go out of this fader right here. And then what I'm going to do is I'm going to hit the negative 6. And you'll see that this thing will pop down to negative 6 right here. It'll pop down right there, and you can just hear it going down to negative 6. But what I want you to do is I'm going to toggle back and forth for that for a little bit. And what I encourage you to do is go do your own version of this in your DAW. Go through and you can write an automation curve for this, or if you want to, like, it's kind of harder, like, now that's the easiest way to do it with an automation system, is basically hop it down, or basically take a clip and copy it and then do clip gain and drop 160 dB next to it, so that you basically can hop back and forth between the two of those. That's why you can kind of get a feel for it. Because what I want you to do is get a feel for what a 6 decibel drop is. So what this is, so a 6 decibel drop is half the value. So is half the, well, in voltage, it's half the value. So if I turn this on, certainly pretty apparent, right? I mean, fairly obvious, yeah? I mean, you can hear it going up and down, like, and would you say that's double the value? Like, is it half as loud? What do you think? What do you think? Is that, so it just doesn't, like, well, 3 dB if you're talking, so Noel, when you say 3 dB is half, 3 dB is half if you're talking about in terms of intensity. It's 6 dB if you're talking about in terms of pressure. So, no, well, yes, it does. I mean, because that's the kind of the weirdness of our ears. So the question was, the reason I'll repeat your question is because when I record this, it doesn't record your guys' voice coming through on this. So on the recordings, it just looks like I'm sitting there quiet. I found that out later recently. But the question was basically, does the frequency change? Or in other words, does the timbre change? So what I'm putting through here, the frequency spectrum is not changing at all. But yet to your brain, you're like, oh, it sounds a little brighter or a little duller. What that means is that that's what we call the timbre. So the timbre or the timbral change does shift a little bit, and that's an artifact of the fact that our ears are very nonlinear. We're going to spend all next week talking about this, is that our ears change when I turn stuff up and turn stuff down. The frequency response of our hearing system changes, and it's really bizarre. So what I'm doing right here is I'm not changing anything but gain. Nothing is changing there at all, but yet you still comes through as being like, it does sound like it kind of changes a little bit, like something changes there. So what we're saying here, and what's also interesting is, again, that we're talking about by 6 dB drop right here is half the original value. So by going to this, to me, it doesn't sound like it's half as loud. It sounds like it's like probably about 3/4 as loud, maybe 2/3. You know, this is hard to, like, that's the thing. And that's where the challenge with measuring human perception is really bizarre, especially because we're all made differently, right? So we come up with these like norms that we all kind of agree upon, that yes, this is loud, this is quiet, but yet we're all physiologically built a little bit different. And so we kind of look at the average of everybody, but yet, you know, some people have like are more sensitive in some areas and other people are more sensitive in other areas. So it's just kind of this like general average we have there. But what I would say is that listening to this, to me, I like, and so other people are saying like Cato said right there, it sounds like about a quarter. For me, it doesn't sound like, it sounds like it gets quieter, but not that quiet. I don't know. To me, it sounds like about a third, it's a third quieter to me. Maybe only a quarter somewhere. That's just my subject. Like that's my opinion. And you could go through. We could do this with tones. We could do it with other things. Actually, let's try it with a tone. Let's do it with a triangle wave. And let's do it at 440. Nice mel. Oops, 449. Sure. Let's make it a slightly sharp A. Bring it up slowly. Make sure I'm not going to be too loud. I don't know. Kind of hard to tell. Like what you think that is. Like what it does it how much how is it half? Is it third? Like let's talk in fractions. Like how much difference does that make? Interesting. Also, to me, the timbre does change, right? So it sounds different. Even though it's the same wave, it just sounds a little bit different between the two of those waves. So interesting. So the point though here is that if I were to do something, let's go back to the pink noise and let's give an example here. If I were to go to, let's just bring this down even further. Let's go to 0.25. So what that means right there is if I'm standing next to a speaker, and we'll say I'm like 5 meters away from a speaker. Actually, let's get closer to it. Let's say I'm 2 meters away from a speaker. If I go from 2 meters to 4 meters, that's the amount of change that gets dropped. But what's crazy is if I go from 10 meters to 20 meters, that's the same amount of drop that it sounds like. So if this sounded like 20 meters, this is what it sounded like at 40 meters. Interesting. So it's that so that allows you to hang on to that perception from along that kind of like bodes that like leans into this our perception of being a logarithmic scale. So what that allows us to do is essentially hear really loud sounds and hear really quiet sounds, or see bright light and see dark light, compressing this into a very, very small system. So that's why our perception, going back to this idea that our perception works on a logarithmic scale for the most part. So kind of interesting. So that's kind of the key takeaway of what I want you to understand for this for this class for today, is that's kind of the basic idea. So if we talk about sound pressure in this free field, so because pressure intensity is proportional to the square of the pressure, the inverse square law becomes inverse distance law when we talk about pressure. So so we say pressure is inversely proportional to distance. So don't write this one down. This is basically like all I want you to do. This just came from the book. Just like I just want to talk about it for a second there, but the inverse distance law, it's basically saying the same thing, but we're talking about it in terms, instead of intensity, we're talking about it in terms of pressure. So that's all we really need to say right there. And I'm not gonna ask you any more questions about this right here. We have basically doubling the sound pressure, distance drops intensity by 2 times. So, but again, this says the same thing. That's basically saying exactly the same thing that we're looking at right here. Sound pressure level. So double the distance, drops by 6 dB. So that's all we really need to say about that one right there. Okay. Let's add a little more complexity to our model. So again, this is just as things moving away. So like also, that's a loaded question or a loaded statement when I'm saying if I move from 10 feet to 20 feet or 10 meters to 20 meters, that the speaker is going to drop by that much. Because again, those are in idealized conditions, that would be the case. But in real world conditions, we actually have reflective surfaces like the ground and other stuff like in the way. So, and other losses, like things like air itself actually absorbs sound at different frequencies, and so the further you get away from it, it will change the frequency response of the sound. And so again, it gets in real world, it gets a little more complex. So we're just talking about in idealized conditions first. So let's take a look at it. Let's add a little more complexity to our system. What happens when we start putting sound fields in enclosed spaces? So this is like more realistic to how we work with our sound here. So what we have here, this plot is also pulled from the book right here. Let's take a look at this. What we're saying here, and they did this in feet down here. Boo, feet. I hate feet. I don't hate feet. I hate the distance feet. So let's we look at our sound pressure in terms of decibels right here. And so this is these are both plotted on a logarithmic scale. So even though this is a 70 to 80 to 90 to 100, this is on a logarithmic scale right here, and this is also plotted on a logarithmic scale right here. But what we see here is if I'm really close to something, so if I'm within 4 feet of a speaker and I get away from it, it's actually steeper than the 6 dB drop right here. It's actually quick. It drops off quicker right there. And I don't really actually remember why that was. Maybe it was explained in the book, but I can't remember why that was. Let me see if I have notes on that. Oh, okay, yeah. Because when you're okay, now I get it. Yeah. So when you're really close to a speaker, so when we get further away from a speaker right here, say we're like in the say 10-foot range from away from a speaker, you can imagine the speaker as being a point source. It's just tiny. It's just this little like we imagine that emanating sphere. But when I'm really close to a speaker, it's actually taking up a much larger space. It doesn't actually act like a point source. So it's actually much larger than it effectively would really be. And the effect is that when I walk away from something that's very close or I get really close to it, it ramps up much quicker because it's effectively larger. It's not a point source anymore. It's actually a lot larger. So when we get to say, and this is, it's per speaker, this is like roughly speaking right here, and we call that the near field. And so for those of you that use like near field speakers, so what they're talking right here is the near field is being pretty much in about the 4 feet range. So if you're within 4 feet of your speakers, like your monitors, if you have studio monitors set up, we call those near field monitors, right? So the near field means it's basically acting not as a point source, but actually as a speaker source, the size of the speaker right there. I can't stand it. I don't work on near fields. Like, so the room I'm in right now, I work in the free field right here, so to speak. So, or far field, we call those mid field. In monitor world, we call those, in monitors, we call them mid field. So my speakers are it's about 10 feet away from me in my room that I'm in right here, my mastering room. So I keep my speakers 10 feet away from me. And for me, I feel like the imaging is better and all these other reasons, but that's just how I roll. Because I have this room that's dedicated for like listening spaces. But as we get to about this 4 feet right here, they're calling it the free field, and they're also calling it the far field. So as we get here, that every time I double my distance, so from 4, 5, 6, 7, 8. So right here, so if I can basically measure that if I go from 4 to 8, it's going to drop by 6 dB. So this is 100, this is 95 right here. So here, 6 dB drop is going to be 6 dB drop every time I double my distance. Cool. And so we call this attenuation as 6 dB per distance doubling. Yep, that makes sense. But then what ends up happening as we get further and further away from our speakers, so this is our direct sound. So the direct sound does drop off. So the sound from the speakers drops off at a constant 6 dB per rate. But what ends up happening is that we get into this reverberant field. We have reflections. So the reflections start to kick in, and then all of a sudden the energy isn't decaying as quickly as we would imagine it to be. So the energy stays in the room. And as a result, and this is going to be different, this curve right here is going to look different for different rooms. Like if you're in a very highly reverberant room, like with a lot of hard surfaces, this is going to flatten out really quick. If you're in a room that has a lot of absorption, like the one I'm in right now, this is going to be a very slow, like it's gonna slow down over here. But basically we have the reverberation, the sound energy in the room. And we're gonna spend a lot of time later in the semester talking about this notion of reverberation. When we start thinking about sound as energy, just purely as energy, that the reverberation is the energy that stays inside the room. It's just sound energy. So that's essentially what this is saying right here. So this is just showing us the whole point of this plot right here is to show us that in real world, things are a little bit more complex. So we start with thinking the idea of the inverse square law, and that every time I double my distance, it drops by 6 dB. But then when we start to add this, like a more complex model of like adding rooms and distances and speakers, that things get a little bit more murky. So that we have to kind of consider that. But it's still worth understanding how sound falls off of a speaker. So in terms of a bottom line here, this is what I want you to remember. Doubling the distance from sound source to receiver results in a 6 dB change, and same for both dB-SIL and SPL. So, because, yeah, we did the math. I didn't do the math on the pressure one, but that's that equation that I didn't really go into. You can work it out if you want to, but you can just trust me on that one. or don't trust me. But if you don't trust me, do the math and you'll prove it to yourself. But for me, I think that's the math is interesting, but it's not as like enlightening as just what the statement says right there. Okay. Let's where are we at here? Let's see. Is that what I have? Cool. So that's what I had for in terms of like content for today. So that gives us a fair amount of time to actually, well, actually, before I move on, any questions on any of the content we just went over on the sound and the free field stuff? So I'm sorry. So you say they're like, can you say that one more time? I like my head, I didn't hear it very well. Yeah. Slightly. So 60 dB is, well, we know that that's half the amplitude. So when you're saying you're doing 60 dB and you're looking at your meters, and when they say 60 dB, so to be clear, when they're saying put your fader or your levels to it's saying minus 60 dB, not 60 dB. So it's minus 60 dB, meaning what that does is that's half the gain. So like if I were to, well, actually, let's just look at that for a second. What do I have simple to do this with? Let's just do it with Wavelab. But okay, I guess I should say that no. So the 60 dB just means half the amplitude. So what they're doing is by saying 60 dB, it gives you a fair amount of headroom. It should give you a fair amount of headroom as you're going along. But when we talk about this in terms of like a mastering context, like the loudness of your track should, like, some people mix it to -6. -6 is ridiculously hot, and I don't really have time to go into it today, but like that's like by modern standards, that's like for the old loudness wars days. We don't really need to be doing that anymore. Sorry, I'm trying to figure out how to succinctly answer your question. Basically, -6 is just a number. It's just so that we use that number a lot because it means half the amplitude. So if I were to, I don't have any in here. Let's create some new ones. And okay, let's create a new one. What I'm going to do is I'm going to create 2 different waves. Actually, I'll just take one of them here. Signal generator. What do I have? Let's do pink noise. Pink noise at level. Let's do it at -6 for right now. Actually, let's just do it at 0. No, let's do -6. Yeah, let's do 0. But I'm not going to play it because I don't want to tear your head off. 1648K, cool. So if I look at this file that I just made right here, actually, let me do it with a sine wave. Let me do it instead with do this with a sine. Let's do it with a sine, just for instance. Frequency. I'm not even going to play this stuff. 261.63. So that's middle C, level 0. So I generate this thing right here, and what I did is if I look at this thing, you can see my sine wave goes all the way up to all the way to the bottom. In terms of what we call headroom, that means there is 0 headroom. So headroom is the difference between your level, your nominal level, and the maximum output. In this case, I don't have any. I have 0 dB of headroom. So if I go over to this, and I'm going to do the level at -6. And you could do this with a fader, but I want to. Oops. Ah, crap. All right. Frequency level -6. -6. Generate. Cool. So we can see the difference here physically. Like, so this is a sine wave at 0 dB output. This is a sine wave at -6 dB output, and you can see that it's half the amplitude. It was reduced by half. So what they're saying there is when you're saying you're doing your stuff at -6, like if you're tracking, for instance, or if you're just like, then I'm not sure if you mean like for your tracks, if you're talking about individual tracks on your multi-track, or if you're talking about your master output bounce. But well, actually, what are you talking about? Do you want to clarify? Okay, let's just continue talking about this. So what it's saying right here is that right now you can see that if what we call my nominal level is being at -6 right here, that means I have 6 dB of headroom. I have a little extra space. So you want to make sure that you have enough room for peaks to happen, for things to happen in that space. So if you're playing, say, like a bass guitar or singing or something like that, that by going down at -6 will give you a little bit of headroom there, so that basically you'll have space for the peaks to live in there. So -6, but for a master output on, say, like your if you're going to post it on, say, Spotify or iTunes or something like that, that actually is way too loud, or even like YouTube is way too loud, because even if you make it out at -6, if you do an average gain of -6 at output right there, they're just going to turn you way down, because like, I'm going to get off on my soapbox here. Like, we'll save that one for critical listening and for mastering, but basically by -6 is way too loud, but it is a good amount. What it does is you want to use them as many of your bits without peaking, and so that's the kind of the idea behind -6. But you're right, -6 shows up a lot in our industry, but the reason is because -6 means half the amplitude. That's why we correlate those two. So -6 equals half in terms of amplitude, because this correlates back to voltage. Voltage uses the 20 dB log, and just because I know this is probably a point of confusion, when we started doing decibels, you're like, wait, didn't you say 3 dB is doubling? You're like, yes, 3 dB is doubling if we're talking about in terms of intensity or in terms of power. But 6 dB is doubling in terms of voltage. And what we normally work with in the studio is voltage, or dBFS right here is also correlates back to voltage. So, pressure. So we usually will talk about pressure. So 6 dB is a doubling of pressure, is a doubling of voltage, is a doubling of amplitude. So, or we could say that -6 is having the voltage, is having the amplitude, or is having the pressure. So 6 dB does show up a lot, and the reason that number shows up a lot is because it means half or double. So 6 dB means doubling, -6 dB means having that voltage. So I think I'll leave it with that one right there. Cool. Any other questions on this? Okay. Yep. No, so like so when you're recording, say, like, so the idea is when you're recording, you always want to set your gain as high as possible without peaking. And the reason being is you want to get the best signal. You want to use all those bits. If you're recording, say, at 24-bit, you've got 24-bit, or like, so back in the old days, when I used to start out, we used to record at 16-bit. And when you have only have 16 bits, you had to record it as loud as possible without peaking, because you want to use all of those bits. When we get to 24-bit, it's not such a big deal. You still want to record with a fair amount of gain. But I mean, to the point where you basically, when you're recording, you want to see, where's my wavelab? You want to see that you have healthy waveform signals. I mean, this is actually a pretty good one right here. So if like you were like, that looks like it's pretty good, I want to see a lot of waveform. What you don't want to see is when you create something that looks like, and I see this happen all the time, like with like, let's do something like, let's do pink noise just as an example, and let's do this something at -20. Oh, let's do -30 just as an example. So right there, so that's a -30 dB like signal right there. If I zoom out right now, and I can't tell you how many sessions I see of student sessions that this is what their like voiceover or whatever. Say, like, let's use your example of a podcast. If your waveform of your voice looks like this in your DAW, that means you recorded way too quiet. Your preamp gain was way too low. So the game is, you want to get your preamp gain as hot as possible, so that you're sitting there and you're using up a lot of these, like using up all the space, but not peaking. And again, if you're working at 24-bit, you have a lot of headroom, so you're pretty good in there. So what I would say is that you always want to record as loud as possible, but then when you bounce down or mix down, you can mix that down to whatever you want to. But like most streaming services, and again, you're going to talk about this in a lot of the other classes, including my other classes, that like something like if you publish to, say, YouTube or to Spotify or to even like Amazon Music Services or Apple, like basically what they do is they turn you down so that you're at -14. So -14 is actually the target level that you're looking for these days. So, and then, so in my case, like this one right here, I could actually render this thing. So if I wanted to render this, where'd my render window go? I can say, I can actually, oh, this one doesn't have it. Do I have normalizing on this one? Actually, I can't do it with this, with Wavelab, but what I can do, but I can do it with Wavelab. It's interesting to me. It doesn't have the ability to, output. So some of them you can output to like minus 14 LUFS. But I use Nuendo as my DAW of choice. And when I export, like say if I'm doing a podcast, I'll export at minus 14 dBFS minus 14 LUFS. LUFS is a little confusing. I'm not going to go into it right now, but you can imagine it closely being dBFS, decibels, minus 14. So the loudness output is going to be at minus 14. Because that 14 means you have 14 dB of headroom and more of this other kind of stuff. So basically what I'm saying to kind of go in a nutshell with your podcast, what you do is you record it as hot as possible and then you bounce it down so that you're just not peaking. And then if you post that on something like Spotify or whatever service, it will take care of the rest of it. They'll actually turn you down and not normalize that for you. So that's the simple answer for right now. It's much more complex than that, and we could go on and on for a few days on that stuff. But which I think is really important. It's just outside of the scope of what we're talking about right now. Cool. Yeah. Okay. Well, let's do this. But yes, like I'm happy. I love talking about all this kind of stuff. Like levels, I know it's super nerdy, but like levels in audio are is a big deal for me. I'm a mastering engineer. That's what I've done for most of my career. And so levels in audio, are my passion. And understanding all this decibel stuff that we've been talking about so far. If you want to become a mastering engineer, you need to know decibels like really, really, really well. And you need to understand all this kind of stuff. So like mastering is not as simple as just tweaking a couple EQ knobs and calling it good and maybe turning on a loudest maximizer. There's a whole lot of digital audio stuff that goes behind the scenes on that you need to understand, and like conversions and gain and decibels and voltage and all that kind of stuff. So that's to me what a lot of being mastering engineer is. So although you can just most of us will just throw up a loudest maximizer on our master fader and call it good, and that's fine too. So I'm not gonna bag on that. So okay, well, let's do this. Let's I want to go through and do some math problems. So what I'm going to do is I'm going to switch over to sharing the screen, and I'm going to just do a bunch of math problems, like some example ones here, doing them by hand on the iPad so that we can actually go through and let me close off stuff that we don't need. And let's do some more math problems because you are going to have to do some of this stuff for this project. Let me create a new one. Cool. Let me switch this over. And what I'm going to do is I'm going to come up with some example problems so we can actually just kind of go through this. Wait, where's my share stuff? All right. Here's my pencil. I got one of these Apple Pencils, and I was like, I didn't think I was really going to use it all that much, but man, it's pretty fun. Like my wife's graphic designer, so we use the iPad for the graphic design stuff. But I think it's pretty fun, like doing the Apple Pencil thing. It's pretty neat. Okay, so let's just do some examples here. So let's do 50 dB is, sorry about my handwriting, is, oops, let me make it brighter. I can't see. This thing is kind of dark. Sorry, I gotta get out of here and turn this thing up. Cool. All right, so 50 dB SIL is what watts per meter squared? So what I'm asking there is like, okay, so 50 dB SIL is what in intensity? So intensity is watts per meter squared. So because I have this right here, because I said SIL, what that does is that implies that, because that's when I had that little picture of the ice cream up there, that basically what that's saying is that it implies that it's a flavor, like that this SIL, sound intensity level, tells us that it's what the reference value is. And SIL is what this means is that I naught equals 1 times 10 to the negative 12 watts per meter squared. Okay, so let's do this. Is that black? Okay, cool. So what I'm going to do is I'm asking for watts per meter squared. So let's set this up. So I go 50 dB Actually, what I'm going to do is I'm just not going to write this. I know I should, but I'm going to write 50 because I'm just going to try and save on some real estate here. Equals, is this 10 log or is this 10 log or 20 log for the equation? What do you guys think? All right, I like that you guys are all guessing on that. So so on this I have a 20, a 20, a 20, and a pressure. And I will say, unfortunately, every one of those answers is wrong. So do you see the I in there? The I in here means sound intensity. So intensity is not pressure. So intensity is the 10 log. So you may have to go back and look at the like it's the tables and some of the information there, but intensity is 10 log. So for this one, because it's SIL, not SPL. If it was SPL, I would say I would use 20 log. But if it's SIL, I use 10 log. So I'm going to use 10 times the log value of, and in this case, right now, I'm just going to write I over I naught for right now. But really, this is right there. But I'm just going to keep it out of the equation right now because it gets a little messy. So the first thing, so what I'm solving for, actually, I'm going to use pink again. I should have a shortcut for that. Maybe there is. This is what I'm searching for right here. That's what I'm asking you for to solve for. So what I'm going to do, the first order event is I'm going to divide both sides by 10. So I divide this by 10 and divide this by 10. I could actually write that like this by 10. So these 10s cancel each other out and I'm left with 5. So 5 equals log of I over I naught. Then I take the inverse log of both of these right here. So I do 10 to the x and 10 to the x on this one right here. And in this case, the log and the 10 to the x cancel each other out. That's the inverse one. And that's the one that everyone has a really hard time with. I get it. And then what I end up with here, so in other words, what this looks like is I over I naught equals 10 to the 5th. So 10 to the 5th, I'm just going to leave it as that, but I could also write it as 1 times 10 to the 5th. It's the same difference. So if I write 1 times 10 to the 5th and 10 to the 5th, that's the same thing. You can just type this in your calculator as 10 to the 5th. But now what I want to do is I'm going to substitute this one equals I over 1 times 10 to the negative 12. Whoops. So now what I need to do is to solve for this I right here, I need to multiply both sides by 1 times 10 to the negative 12. So basically, I'm gonna erase this because this is a little harder to see. Actually, let's just erase this whole thing. Pen. So equals I over 1 times 10 to the negative 12 watts per meter squared. Because we know that I naught right there is because we're talking about SIL. What is 1 times, does anybody remember, what is 1 times 10 to the negative 12? What does that represent? What does that mean, 1 times 10 to the negative 12? Yeah. Yeah, exactly. You're right. But what is that? What does that refer to? Like, what does that mean? Like, what's the meaning behind that number? Didn't remember what that is? That's the threshold of hearing. That's the quietest sound you can hear. So we use that. That's the reference. So what we're doing right now is when I say dBSIL, 50 dBSIL, meaning what is the sound now? Remember, always ask yourself, what's the comparison? We're comparing two numbers. A decibel is always a comparison. So when I say 50 decibels, I'm saying what is the sound now compared to the quietest sound that you can hear? And that's, in this case, it's 50 decibels. So what we're doing is 50 dBSIL. So what we want to do is we want to solve for 50 dBSIL means what in terms of intensity? So what I'm asking you is 1 times 10 to the negative 5, or 1 times 10 to the 5th equals I over 1 times 10 to the negative 12. So to keep working on the algebra here, what I'm going to do is I'm multiply by both sides by 1 times 10 to the negative 12 watts per meter squared. And then multiply this side by 1 times 10 to the negative 12 watts per meter squared. So these cancel each other out algebraically. And I'm left with just rewriting this thing out. I'm just going to write it out cleaner here. Equals 1 times 10 to the 5th times, I'll put that in parentheses just to make it a little cleaner, 1 times 10 to the negative 12. It's hard to see that negative right there. And at this point, what you could do is just basically go in and type this into your calculator. So what I would do is I would do 1 EE5 times 1 EE negative 12. There's also a shortcut way if you have some math chops. Knowing how exponents work here is that basically what I can say is that 5 times, I add the exponents in this case. So I'd add a negative 12 plus 5. So 5 minus 12, which is 7. So it's 1 times 10 to the 7th. That's the answer. Oops. Sorry, 1 times 10 to the negative 7th. Let me erase that. Let me clean that up. Well, that's big. It's fine. I'll just get rid of this. Sorry, I'm still not that fast with this stuff. Get better. So the answer is 1 times 10 to the negative 7th watts per meter squared. So that's our answer right there. Which is also, I could write this as 0.0000001, 2, 3, 4, 5, 6, 7. That's the same answer right there. So if you type it in your calculator, you'll probably end up with this one right here. And that's fine. Cool. Yep. There it is. Yeah, Noel. So Noel wrote it up in the chat right there. So saying like, oh, you can do math with the exponents. So 5 minus 12 equals negative 7. So that's exactly what I was doing right there too. So but if you're uncomfortable and unfamiliar with doing math and exponents, use your calculator and trust your calculator. And then I would also say ask each other. So just real quick, a note on the Discord. So I love it when people are helping each other out, and I want you to. That's the whole point of it, is I want you helping each other out. But what I don't want you doing, and you cannot do, is give answers out. So you cannot post answers to the homework questions on Discord. I'll come after you if you do that. So don't post answers. So if you want to like talk about, if you want to show how to do something like what I'm doing right now, use different numbers than what you're doing. So if you want to show somebody how to do the math on the homework and you're helping them out, just change the numbers to be different numbers so that you can go through. So you're not actually giving the actual answer on this. So please be aware of that. Because that's considered cheating if you share answers. So, but I want you to work through all this stuff together. Of course, that's the whole point. I want you to do it. So, and for those of you that are really comfortable with this math, please chime in and help each other out, because I know this is hard for a lot of people. Okay, let's do another one. Or I guess before I move on, I know that this is pretty ugly looking on the screen there, but is there any questions on what I did there? Okay, well let's do another one. So let's do something like this. Let's do like 0.2 Pascal, or like, okay, let's do this one. 0.02 pascals is whoops. dB SPL. SPL. So 0.2 pascals is how many dB SPL? So what I'm asking you, because once again, because I'm using a flavor, so you have decibels. Decibels are just a raw comparison. Whenever I say decibels, all I'm doing is comparing. When I say dB SPL, what I'm doing is I'm implying the use of a reference value. That's really important concept to understand there, is that when I say dB SPL, anytime there's a dB something, dBu, dBm, dBV, dB SPL, dBFS, I'm implying a reference value. So in other words, the denominator in the decibel equation is known. And in this case, we know that to be, in this case, because we're talking about SPL, go back to if you need to go back in your notes and go back in the book, it says 2 times 10 to the negative 5 pascals is going to be, is the reference value. So let's do it. So what I'm going to do is I'm going to do dB SPL SPL equals 20, because this one is the 20 log P over P naught. And in this case, P naught equals 2 times 10 to the negative 5 pascals. And I know that because, well, it's given to us. That's the whole point of SPL, implies this down here. So SP, the pressure, implies that this P naught is 2 times 10 to the negative 5. And now we just do a quick quick substitution in there. So I'm going to write again. I'm just going to write dB SPL equals 20 log, and then what I'm going to do is I'm going to put 2 times 0.02 pascals on the numerator, because that's what this is right here, and this one is this one down here. So this is going to go 2 times 10 to the negative 5 in this case. So this is a little bit trickier for me to do in my head, but what I'm going to do here is I'm going to write this as 2 times 10 to the negative 2. Well, or yeah. Actually, let's do it on the calculator, just so we can see this thing. So no, actually that's kind of hard to do on here. So I'm just gonna go. So what I'm gonna do it on my calculator. I wish I could share this one easy, but I will go. Normally this one I could do by hand, just do in my head, but I'll do 2 EE. Or actually, I'll just do 0.02. 0.02 divided by 2 EE negative 5 equals 1,000. So equals 20 log of 1,000. And at this point, we actually could do that one in our head. But if you're not comfortable with it, just prove it yourself. Hit the log button, and we end up with 3. So 20 times 3 equals 60. So dB SPL equals 60. And you're like, well, is it pascals? Is it dB? What is it? And you're like, no, it's because this is a pascal. This is a pascal here. So those values, those actually cancel each other out. So remember, decibels by themselves are straight up dimensionless. So cool. All right, my friends. Like what I think I'm probably going to do is I'm going to put out some so this should get you going enough for some of the homeworks. It's algebra, and I know it's hard. So I can help out. Like, hit me up if you have questions. But before you hit me up, and I'm okay. I love helping you out. But ask each other first. Ask on Discord for the help on this one, on any of the questions there. Ask for help on that, and I will be active on that platform, because the problem is if you ask me and I help you out, it doesn't help out anybody else. And so what we do, the cool thing is if we do this on Discord or on a public forum or on the discussion in Canvas, it allows other people to learn from our discussions here. So and also even make them searchable. So I would request that you don't just hit me directly. I'm happy to help out for sure. But let's do it on a platform where we can work as a group. And on the flip side of that is put it out in the ether and ask if you actually understand this math. Please help each other out and try to explain it. And I know it's very difficult to show this also, like in Discord, right? When you're doing these equations in Discord, is a very difficult way it's not a very good system for doing that. So, but if you want to do screen shares or hold up pieces of paper and screenshot it or something like that, or just however you want to show how to do this, let's work through that. That's like math and text editors and IMing is kind of difficult to do, but I think we can do it. So I'm around. I'm going to post up the next homework. It's going to have a fair amount of decibel stuff on it and a little bit of what we went on today. But other than that, I think we're going to go ahead and call it there. So with that, my friends, I will go ahead and stop the recording. And yeah.